Kirchhoff's laws. Kirchhoff is a German scientist, and he found out two laws to solve the complicated circuits. The two laws are: number one, Kirchhoff's first law, otherwise called as point law, otherwise called as current law. And similarly, the second law, Kirchhoff's second law, or this can be called as a mesh law, or this can be called as a voltage law. Now, Kirchhoff's current law. Kirchhoff's current law states that in any network, the algebraic sum of the currents meeting at a point or junction is equal to 0. In other words, the total current leaving the junction is equal to the total current entering the junction. Just see the figure here. The A is the junction, and I1 as well as I5 are the currents leaving the junction. Similarly, the currents I2 and I4 are entering into the junction. I3 is also leaving. So the current leaving the circuit is equal to the current entering the circuit. So we can write it in algebraic form: minus of I1 plus I2 plus minus of I3 plus I4 minus of I5 is equal to minus I1 minus I3 plus I2 plus I4 minus I5. So by the way, I2 plus I4 entering the circuit is equal to I1 plus I3 plus I5, that is leaving the circuit. So this is the Kirchhoff's first law. So in a particular junction, the current leaving the junction is equal to the current entering the junction. Now let us go to the second law. In the Kirchhoff's second law, or the mesh law, states that the algebraic sum of the potential, that is the product of the current and resistance in each of the conductors in any closed circuit in a network, plus the algebraic sum of the EMFs in that particular path is equal to 0. Once again, it states that the algebraic sum of the product of current and resistance, IR, that is more or less the voltage, in each of the conductors. These are all the conductors. In each of the conductors, in any closed circuit in a network, plus the algebraic sum of the EMFs. This here in this circuit, this is the EMF. Algebraic sum of the EMFs in the path is equal to 0. So sigma IR plus sigma EMF is equal to 0. Let us take the Wheatstone bridge network. The figure shows this circuit is called as the Wheatstone bridge network. And here A, B, C, D, E, F. These are all junctions. And R1, R2, R3 and R4. These are all the various, and also R5 is also different arms. And here the voltage applied across the circuit is equal to E. So we can form different closed circuits to find out the values. And to find out the different closed circuit, we can see, first you put the circuit, and here by using the Kirchhoff's first law, the current meeting at the junction is equal to 0. So in this particular circuit, current is coming from this circuit, current is leaving from this circuit, and current is leaving from this circuit. So the current leaving the junction is equal to the current entering the junction. Now we can mark the currents as I1, I2, I3. So the total current from the source, that is the voltage source, is equal to I1. This I1 divides itself into I2 and I1 minus I2, because I1 is entering, I2 is leaving, so the remaining thing I1 minus I2 is flowing through this circuit. Similarly this junction, similarly here we can have a closed circuit. See, F, A, D, C, E is a closed circuit. Another closed circuit is A, B, D, A. Another closed circuit is B, C, D, B. So, by writing the equations for the three different circuits, we can find out three different equations, and by solving the three simultaneous equations, we can find out the values of I1, I2 as well as I3. Thank you. Determination of sign. That is, start from the positive terminal of the battery, it reaches the negative terminal. And it is termed as fall-in potential. That is, positive to negative is a fall-in potential, and it will be represented by the negative sign. In case if we have taken the circuit in the reverse sense, negative to positive, raise in potential, so we can use a positive sign.